In this video, we solve problem 13.7.028 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to find a set of parametric equations for the tangent line to the curve of intersection of the surfaces at the given point. We're asked to enter our answers as a comma-separated list of equations. Okay, so we've got this guy and this guy. Now, over here, notice that there is no x, so that makes this a cylinder. Notice also that z is raised to the first and y is raised to the first, so that's a plane. In the yz plane, what we would see is this. Here's z versus y, and yeah, I'm just writing it this way because that's exactly what we're going to see in three-dimensional space with our right-handed coordinate system, right? When y equals 9, z equals 9, or excuse me, when y equals 0, z equals 9, and when y equals 9, z equals 0. So what we would see is this line, but it's sort of coming out of the page at us. If the positive x direction is like this, coming straight out of the page like this at us. So if you've got your y-axis, and then your x-axis is here, and the z is just going straight up from that. Here's x, and then y, and then z. The plane z equals 9 minus y is going to look just like that, but it's going to come straight out at us because the x direction is coming straight out at us. So that might look like this. I've got my sticky notes here. So you've got this plane that's coming straight out at you. Now, at the same time, around this z-axis, you've got an elliptic paraboloid. So we're asked to find a set of parametric equations, of the tangent line to the curve of intersection of the surfaces at the given point. So the first thing I would do is I would find that curve of intersection of the surfaces. And this first surface is z equals x squared plus 9, our elliptic paraboloid that opens on the positive z-axis. I said x squared plus 9, x squared plus y squared. And then we're taking this and we're intersecting it with a plane that crosses at z equals 9 and y equals 9. So we're going to have a plane, and I think I probably need to make my z or my elliptic paraboloid a little bit bigger, sort of illustrate what's happening. This plane is going to intersect this elliptic paraboloid on a curve because you've got this guy and it's sort of coming out of the page, and then you've got an elliptic paraboloid sort of around it. And what we end up with is something that looks kind of like this. This is what I would expect. And I'm trying to draw that plane on with some perspective now. I'm not very good at it. There are a lot of artists in my family, and I wish they were here to help me because I can see it in my mind. I just can't draw it on my paper. But I hope you get the idea. What we're going to see is an ellipse, basically. We're going to see this plane is intersecting this elliptic paraboloid on an ellipse, and we're saying at a particular point on the ellipse, where x equals 3, so we're going to be out this way, y equals -1 and z equals 10. We're saying what is the tangent line there, that location, or what are the parametric equations for the tangent line at that location? So the first thing we need to do, the plan is to find parametric equations for this curve of intersection. So basically what we want is we want r of t, and this is a curve in three-dimensional space, so it's going to have components x of t, y of t, and z of t. So we want that. And then once we have that, we can find the t value that corresponds to that location. And then once we're at that location, we know the tangent line is going to have a direction vector equal to the derivative of this function. Well, we're going to get there in a little bit. So we'll take the derivative of this. It's going to give us a tangent vector. We've got a point and a tangent vector or a direction vector of a line with a direction vector of a line and a point. You can write down the equation of the line. But first things first, let's find the parametric equations of this point of intersection, or this curve, excuse me, of intersection. So I'm trying to find parametric equations of that ellipse right there. Okay, well, I know that on this plane, z is equal to 9 minus y, and on the elliptic paraboloid, z is equal to x squared plus y squared. So I can set this z value equal to this z value, and that is where we'll have this curve of intersection. So we're setting z1 equal to z2. We've got x squared plus y squared equals 9 minus y squared, or excuse me, 9 minus y. And it's not obvious, but that's either a circle or an ellipse. I think it's actually a circle now that I'm seeing it like this. But it's not a circle centered at the origin. In order to write this circle in standard form, I need to move all the y's to one side. I'll leave that 9 over there. And then we need to add something here to complete the square so we can find the center of that circle. Well, in order to find that number, we take the number in front of the y, that's our b. You take half of that and you square it. 1/2 times 1/2 is 1/4. Add that 1/4 over here and add that over here. Maybe we need to get a common denominator. And so this equation becomes x squared plus this perfect square, two numbers that multiply to give me 1/4 that add to 1, or 1/2 and 1/2. And then over here we've got 36 plus 1 over 4, or 37 over 4. So this is the equation of that ellipse, but it's not taking that z value, the fact that z is changing, into account. I said an ellipse again. It's a circle, which is a special type of ellipse. But now I want the equations of that circle, the parametric equations of that circle. So I can write down this r of t. Well, typically what we do if we want parametric equations of a circle is we let x equal cosine and y equal sine. If we have a radius over here, in this case we do, the parametric equations for x and the parametric equation for y, they're going to involve that radius. So I need this to be the radius times cosine of t. And if the radius squared is 37 over 4, that means our radius must be the square root of 37 over 2. So we'll have the square root of 37 over 2 times cosine of t, and that's going to take us around this circle. Now, for the y value, so I want this squared plus this squared to equal r squared. So I need this to be r cosine of t, and then I need y plus 1/2 to equal r times sine of t. So to find the y value, we take that y plus 1/2 and set it equal to r times sine of t. And when we solve for y, we end up with y equals negative 1/2 plus r, which is the square root of 37 over 2 times sine of t. Okay, so that's our x value and that's our y value. Now the whole time we're on this circle, where this plane intersects this paraboloid, the z values are also changing. So in order to find the z values, well, I will just use this second equation. It's going to be the easiest one to simplify. Z is equal to 9 minus y. So I would use this as my y here. So I'm doing 9 minus this. 9 minus a negative 1/2 plus square root of 37 over 2 times sine of t gives me 9 plus 1/2. I'll just write it as 9.5 minus square root of 37 over 2 times sine of t. Okay, so that was a lot, and my paper is a little bit of a mess, but I hope you get the idea. These are the parametric equations of the curve. So we're going to keep going. Now this is how we describe that curve. As t increases, we're going to go around and around this circle. So x was r times cosine of t, y was r times sine of t minus 1/2, and z was 9 minus y. When we subtract this from 9 and simplify, we get this. And this is going to work for all real numbers t. We would just go around and around the circle. And the question is, what value of t, or what is one value of t that would land us at this location? X equals 3, y equals -1, and z equals 10. Well, in order to find that out, I need to set this equal this x of t, y of t, z of t to equal 3, -1, and 10. And so from here, we've got x equals square root of 37 over 2 times cosine of t. We're going to set that equal to 3 and solve for t. And so we'll have cosine of t equals this times the reciprocal of this. So we'll have 3 over 1 times 2 over the square root of 37. So we'll have 6 over the square root of 37. So t is the inverse cosine of that number. And then I claim that if t is the inverse cosine of that number, then y is going to equal -1. You might say, how do you know that that's true? Let's see. Y evaluated at the inverse cosine of 6 over square root of 37 is square root of 37 over 2 times sine of the inverse cosine of 6 over square root of 37. And we're subtracting 1/2. Now that's kind of an ugly expression. And that's okay. We can work that out. Just going back to a little bit of trig. The inverse cosine of 6 over the square root of 37 is an angle. Arc cosine, arc sine, arc tangent, they always give you angles back. And they're saying, I'll call that angle theta, I'll call that angle t. So t is equal to this if the cosine of t is equal to this. So that's adjacent over hypotenuse, 6 over square root of 37. And then the other side of the triangle can be found using the Pythagorean theorem. If this side is called, let's just call it the opposite side, this side squared plus this side squared equals that side squared. So I must have 6 squared plus the opposite side length squared equals the square root of 37 squared. So that's 36 plus the opposite side squared equals 37. Because the opposite side squared must be equal to 1. We subtract that 36 from both sides. So the opposite side must be equal to 1. Okay. So I want the sine of that angle t now. T is the inverse cosine of 6 over square root of 37, whatever that is. We could use our calculator to find out what that is, but I don't even need to. I can draw this triangle, and now I want the sine of t. That's going to be opposite over hypotenuse. So that makes this sine of t equal to 1 over square root of 37. And this square root of 37 and that square root of 37 reduce, and we just end up with 1/2 minus 1/2. Ooh, which is 0, not -1. Did I make a mistake somewhere? It's not giving me what I want. Okay, so I'm going to change these parametric equations just a little bit. And you might be saying, how can you justify this, Ms. Townsend? I can justify it. I'm just going to change that sign to a negative sign. And then we'll have -1/2 minus 1/2, which is -1, which is what we want. And if you're saying to yourself, what? Why can you just do that? The reasoning is this. I've got x squared plus y plus 1/2 squared equals r squared. So x, if I let x equal r times cosine of t, and I let y plus 1/2 equal r times sine of t, that will satisfy this equation. And that's what we did, and that's how we ended up with this. But I could have just as easily let y equal the negative r value times sine of t, because negative r times sine of t squared is r squared sine squared t, just like positive r times sine of t, quantity squared, is r squared sine squared t. So really this y plus 1/2 could have been plus or minus r times sine of t. It's just typically just r times sine of t. And the same is true for the x. It could have been plus or minus r times cosine of t. Either one would be fine, because when I square that and I square that, I still get the 37/4. So I'm going to make that r, this negative r sine of t minus 1/2, and then we'll have -1/2 minus 1/2, which is -1, which is what I want. And then let's see what z is now. Ooh, and if I change the value of y, that means I need to change the value of z, parametric equations for z. If I'm making that a negative, I need to make that a negative, which makes this a positive. Okay. So now it's a positive now. So now we'll evaluate that expression at the inverse cosine or arc cosine of 6 over square root of 37. That's 9.5 plus square root of 37 over 2 times sine of the inverse cosine of 6 over square root of 37. And again, that's t. Sine of t turned out to be 1 over square root of 37 using this triangle. And then when you multiply these guys together, the square roots of 37 reduce, and you end up with 9.5 plus 1/2, which is 10, which is what we wanted. So when t equals this, and y is given by this function, and z is given by this function. Y is equal to -1, and z is equal to +10. Okay, so that was a lot of work. Just to verify that this point is on this curve. Okay, so now let's go back to the question that we were asked. It says, find a set of parametric equations for the tangent line to the curve of intersection of the surfaces at the given point. And then asks us to enter our answers as a comma-separated list of equations. So I need the tangent line to this curve. In order to find the tangent line, I need to find a tangent vector. To find the tangent vector, I'll just take the derivative of this function. So we're going to compute r prime. Derivative of cosine is -sine. Derivative of sine is cosine. And then, of course, the derivative of that constant is 0, and the derivative of that constant is 0, and the derivative of sine is cosine again. Now we want to evaluate this at t0, where t0 is the particular value of t that lands us at this location. So this is really x of t0, y of t0, z of t0. And t0 turns out to be this inverse cosine of 6/√37. So when I evaluate this at t0, I need cosine of t0, I need sine of t0. Figure out what those guys are. Okay, at t equals t0, cosine is 6/√37 by design. So this is -√37/2, and cosine was 6/√37. Of course, the square roots of 37 reduce. Oops, that one's not negative, it's positive. And so we end up with 6/2, which is 3. -3 here and +3 here. And then for sine of t0, remember what we did before with this triangle. Sine of t0 ended up being 1 over the square root of 37, because it was opposite over hypotenuse. So this gives you a -1/2. And that is a tangent vector. So the direction vector for that tangent line can be any constant times this tangent vector. Usually we like that leading coefficient, or not leading coefficient, but usually we like that first component of the tangent vector to be a positive integer. So I think I'll just take this and I'll multiply by -2. It's still going to give us a vector that's tangent to the curve. We just flipped it, so it's going the opposite direction, and we made it twice as long to get rid of the fractions. And so we get 1 there, and 6 there, and -6 there. So that's your A, B, and C. And remember from our study of lines at the very beginning of the course, if we want a line that passes through x0, y0, z0, and has a direction vector, V with components A, B, and C, the parametric equations of that line are given by this. You start at x0, y0, and z0. And then to get to the next x value, you add a times t. Because this says go a units in the x direction to end up at your next location. So if t is equal to 1, we just go from x naught to x naught plus a. If t is equal to 2, we'll go to x naught plus a. So we'd end up with x naught plus 2a. As t takes on different values, you end up going back and forth along this line. Similarly, we're going to add bt to that parametric equation for y and ct to the parametric equations for z. X naught, y naught, and z naught were given to us. That's these three numbers. This is our x naught, our y naught, and our z naught. So 3, -1, and 10. And then we are adding a, b, and c times t. A is 1, b is 6, and c is -6. Now I think WebAssign doesn't like you to explicitly mention the dependence on t. So what you would enter in WebAssign is x equals 3 plus t, y equals -1 plus 6t, or if you prefer 6t minus 1, same thing, and z equals 10 minus 6t. Instead of adding a -6t, just subtract 6t. And again, if you're saying to yourself, what is that? It's the tangent line to this curve of intersection at the particular location. X equals 3, so we're over here. Y equals -1, and z equals 10. So we try to draw a picture of a tangent line. These are hard to draw. It's hard to draw 3D lines in 2D. So we've got a tangent line here, and the point of intersection is x equals 3, y equals -1, z equals 10. And the tangent vector to that line was given by this. And the way we found that was we first came up with parametric equations for that curve of intersection by setting the z's equal to each other. Then we noticed that that was either an ellipse or a circle. We complete the square and we see it's a circle. And then one of the best ways to parameterize a circle is to let x equal r times cosine of t, and let y, or y plus the constant in this case, equal r times sine of t. And either one of those could be plus or minus in order to satisfy those equations. So we used those ideas to write x of t and y of t down. And then once we had y of t, we also knew that z was equal to 9 minus y of t, so we computed what z would have to be. Then we went over here and we said this is our r, and then we ensured that that parameterization of the curve actually worked, and it actually didn't work at first. With this as a positive square root of 37 over 2 times sine of t, we didn't get -1, we got a 0. But when we flipped that sign, it gave us the -1 that we needed, and it would still satisfy the original equation of that circle of intersection right here, which is also right here. Okay, so we got our parametric equations of that circle, that slanted circle in 3-dimensional space. It's going to look like that. And we said if we want the tangent line to that, first we need to find a tangent vector. So you compute r prime, and then you evaluate it at the t value that corresponds to that location, x, y, and z. So when t is equal to this, we're at this location. You can think of t as time if you want to. So you're going around and around at different times or at different locations. At this time, we're at that location. So we find the a tangent vector at that location by evaluating r prime at t naught. And then we said, We don't want that fraction there. So let's multiply to make this first component a positive integer as small as possible. Multiply by -2 to make that a 1. And then once we had v, now you have v and you have x naught, y naught, and z naught. So you just substitute x naught, y naught, and z naught, and a, b, and c into the equations, parametric equations, excuse me, of a line that we talked about way back in our first chapter in Calculus 3.